Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids, math, science, history, unraveling the mystery that all started with a big bang.
Hello everybody. Today we will be talking about the different factors that can affect the rate of a reaction. And will these factors increase the rate, slow it down, so on and so forth. So, technically, there are four things that can have an effect on the rate. One is the nature of the reactants, two, the concentration of the reactants, three, the temperature, and four, the presence of a catalyst. For this video, we will only be talking about the concentration, temperature, and the addition of a catalyst because you can apply all three of those to most reactions, whereas the nature of reactants can't really be generalized for most of the reactions that happen. So, first off, we're going to talk about the concentration. What is concentration though? Generally, it is defined as how much of an object there is in a given space. It's practically the same in chemistry on the fact that concentration is usually measured in molarity or the amount of moles of a substance over the total volume of the container. So how does concentration affect a reaction's rate? A reaction has two components, the reactants and the products. Think of the reactants as employees or workers and the product is their objective or goal. For example, if we say that there are 5 carpenters working together to build a wall and in total it took them 5 hours to make it, if we increase the amount of carpenters, naturally the time it takes for them to build the wall will decrease. This is the same with a chemical reaction. The more concentration of the reactants there are, the faster the rate of the reaction. Moving on to the equations, we have the rate law equation or simply the rate equation, which is rate is equal to K times A times B, which was derived from the reaction A plus B equals C, where K is a constant dependent on a temperature, A and B are the concentrations of the reactants. If we say that the temperature is at 25 degrees Celsius, then the K for the reaction is 0.01. Assuming that the concentrations of A and B is 5, while also assuming A is first order and B is second order, then we get a rate of 1.25 m per s or molar per second. To prove that increasing the concentration increases the rate, we simply need to plug in a value of concentration of A and B that are both higher. The example is if we plug in 6 molar, then we get 2.16 molar per second. For temperature on the other hand, it doesn't directly apply anymore to the association we had with carpenters in a sense that if you increase the temperature, then the carpenters will get the job done faster. No. You see, if you heat something up, then the kinetic energy of the molecules of that thing goes up and they move a lot more, or in other words, they get excited. For carpenters on the other hand, think of heat as food or drinks for the weary construction men. If you give them more food or more to drink, then they will have more energy, and more energy means they will finish the job a lot faster. Now, we've talked about the rate law equation and how it relates to the concentration of the reactants. On the topic of temperature though, we will talk about the equilibrium constant or K and how it's computed through the Arrhenius equation for activation energy, or K equals AE raised to negative EA over RT, where A is a frequency factor, E is a mathematical constant, EA is the activation energy, or how much energy you need to get the reaction going, measured in joules per mole. R on the other hand is the energy constant, which is approximately 8.31 joules per mole Kelvin, and T is the temperature in Kelvin. I won't be discussing too much on the equation itself, just that temperature can increase K, which if plugged in the rate law equation will increase the overall rate of the reaction. After some simplification, the equation will look like this. ln of K equals negative EA over R times 1 over T plus ln of A, which can be graphed in the form of y equals mx plus b. If we put it into a graphing calculator, the graph will look like this. Now, we can see that as 1 over t increases, then the ln of k decreases, which means that if t increases, then ln k or k goes up. This is how you can generalize that if the temperature goes up, then the overall rate of the reaction goes up. Moving on to the last factor, the addition of a catalyst. What are catalysts to begin with? Catalysts are either organic or inorganic molecules that have an effect on the rate of a reaction. A catalyst in hindsight is added to the reactants and it increases the rate of a reaction. This is explained as a catalyst decreases the activation energy of a reaction by introducing more molecules with the high kinetic energy to the reaction. Also, catalysts later formed as a part of the products, meaning, unlike the reactants, catalysts are not used up in a reaction. If we go back to the Arrhenius equation for activation energy, K equals AE raised to negative EA over RT, and if we decrease the actual activation energy required, then K increases, which once again leads to the final rate of the reaction increasing. If we take a look at this graph, we can see that in a normal reaction, without the addition of a catalyst, this is the energy it takes to proceed to completion. If we add a catalyst, on the other hand, the activation energy decreases, causing more molecules to make the cut and react to form the products. In a last relation to our Carpenter paradigm, a catalyst is a sort of shortcut or an alternative method for doing their job. It presents itself as the easier and faster way to accomplish things, which makes life better for everyone. A word of caution though, catalysts don't affect the equilibrium of a reaction. They just speed up the forward and backward reactions if it's a two-way reaction. Anyway, this is the end of the video and I hope you all learned a lot.